This lesson is about specific latent heat, and in the last lesson we briefly covered what latent heat is, so let's just do a recap of that. So let's recall from last lesson that latent means hidden, and if we drew the graph of temperature against time, so let's remember that if we're heating something up, the temperature is going to increase. There'll be a point where it doesn't increase, where it stays the same, and then it will start to increase again. So remembering that at this point here, that this is where it changes state. Okay, because we can tell that from the graph. When it's flat on the graph, that is where the substance is changing state, and the latent heat is the energy transferred when there is no temperature change, okay, because it's hidden, because we're not seeing a change that's happening there. Okay, so that's the recap from last lesson. However, for today we're talking about specific latent heat. Okay, and because it's specific, that means that we have a definition that we need to work from. So for specific latent heat, it's still talking about this energy, but the definition is the energy transferred per kilogram when a substance changes state. Okay, so we're starting to put it into a quantifiable and measurable situation here, because we're saying how much energy is transferred for every kilogram of a substance when it changes state. And we do have an equation, and it's an equation you get given. So it's on the sheet that gets inserted into your exam paper. So energy equals mass times specific latent heat. Okay, so this is an equation you get given, and in symbol form it would be E equals M for mass, L for latent heat. So there are two types of specific latent heat, and this depends on which state is changing. So let's first of all think about the specific latent heat of fusion. Okay, so the fusion bit refers to the change of state where we're going from a solid to a liquid, or if we were going from a liquid to a solid. Both of those things, it's that change of state that would be happening. Okay, so this is the energy that would be transferred per kilogram of a substance when it goes from a solid to a liquid, and this happens at the melting point. Then we have the specific latent heat of vaporization. And some of you might have already guessed that this is where we go from a liquid to a gas, or from a gas to a liquid, and this happens at the boiling point. So at these very specific temperatures where the graph would be flat. So if you were at school now, we would do the practical with you. Okay, so I'm just going to run through how we could measure these things. So for the specific latent heat of fusion, we want to know how much energy we are putting into something to make it melt, basically, in a really basic way. Okay, so if we were measuring the latent heat of fusion, so L for latent heat and then a little f to show that it is for fusion. So what we would do is we would have a beaker, and in the beaker we would put a funnel, and then in that funnel we would put a heater surrounded by ice. Okay, and the heater would go to a joule meter. So we might remember from the specific heat capacity that a joule meter measures energy, because energy is measured in joules. Okay, so we've got a heater in a beaker of ice, in a funnel of ice, sorry, and then in a beaker. So what we're going to do is we are going to turn the heater on. Okay, and when we turn the heater on, it's going to heat up, obviously, and it heating up is going to melt some of the ice. I'm going to leave it for a bit, so let's say 10 minutes. After 10 minutes, turn it off. Okay, so it's as simple as that. Turn a heater on, turn a heater off, but that's not going to get us a result. So if we look to our equation, if I want to work out L, I need to know E and I need to know M. So the way that I'm going to find out E, the energy, is by looking at my joule meter. So I would record the number of joules shown on the joule meter. Okay. The other thing I need to know is M, which is the mass, and we should know that mass is measured on a balance. So we could say measure the mass of the liquid in the beaker on a balance. So two things to note about this. How do we measure a liquid that has been collected in a beaker? Because surely it's going to measure the beaker as well. Well, when we did about density, we put a beaker on a balance and turned it on, and then added the liquid so that it only measured, it started from 0 when we turned it on, and then it only measured the stuff that was added. So you could pour this into a beaker that's already on a balance. The other thing is you could measure the beaker and the water, and then you could pour the water out, dry the beaker, and then measure the beaker again so that you have the mass of an empty beaker. And then if you take that away from the mass of the beaker and the water, you would be left with just the mass of the water. The other point to make is that some ice would melt at room temperature anyway. So we could do a set of this without the heater inside and measure how much water is in the beaker anyway at room temperature, and that would work as a control, and we could take that from our final mass so that we knew how much had melted just because of the heater. So that's a bit of a higher level kind of question that you might get asked. So on to specific latent heat of vaporization. Well, having talked about this, you might be able to work out what we're going to do here. So we're going to start, funnily enough, with a beaker of water. And in the beaker of water, we're going to put a heater that is going to be connected to a joule meter. So yet again, we are looking at how we can measure our energy. And we would sit the beaker on top of a balance. And this would tell us the mass of the beaker and the water. So what we would do is we would measure the start mass. We would then turn the heater on and bring it to the boil. And then after a certain amount of time, let's say 10 minutes again, we'd turn it off. After 10 minutes, turn it off. And then it's going to be very similar to this. We're going to record the number of joules. On the joule meter. Measure the new mass. So see what it says on the balance. And then we would find the difference. So the reason that we would find the difference is if we think about what we know about things boiling. We've got a liquid in here, we've got water, we're going to heat it up, we're going to boil it, and that steam is going to leave. And because it's going to leave, the mass of water that is on the beaker is going to decrease. So let's say that we had 35 grams at the beginning. At the end, we might have 31 grams. So we would find the difference between those two, so 4 grams, and that would be the mass that we would use. And then we would find the energy from our joule meter to be able to find the specific latent heat. Right, we're going to go through some of the questions. Make sure you've got a highlighter, make sure you've got a pen, make sure you've got a calculator so that we can go through the questions effectively. So remember that we highlight the data that we've got to then help us pick out the information really easily. If we're going to do a calculation, we write out the equation, then we substitute in the values, and then we calculate. Okay, so use the following information to calculate the energy needed in the following situations. Gives us a table of data, material of water, has a specific latent heat of fusion of 334,000 joules per kilogram, and lead has a specific latent heat of fusion of 22,400 joules per kilogram. How much energy is required to convert 1 kilogram of water from ice at 0 degrees Celsius to water at 0 degrees Celsius? So it's told us it's specific latent heat of fusion, and we know from our equation earlier that that is energy equals mass times specific latent heat. How much energy is required to convert 400 grams of lead from a solid to a liquid at the same temperature? So the first thing to mention with this is it's given us 400 grams, not kilograms. So the first thing we need to do is convert that into kilograms. The way that we convert from grams into kilograms is by dividing by 1,000, which some of you will just do in your head. Whoops. So 400 divided by 1,000 is 0.4. So I would just write that 0.4 here just to remind myself. How much energy is given out when 37 kilograms of water freezes at 0 degrees Celsius to become ice at 0 degrees Celsius? Ooh, massive number. So we could do one of two things here. We could write down 12,358,000 joules, or we could do something which I would think would be better, which is to put it into standard index form. So I would 1, 2, 3, 4, 5, 6, 7, and then I would do it to two significant figures, 1.2 times 10 to the power of 7 joules. joules. The reason that I would say this is because otherwise if you miss a 0 off here, then you've completely changed the number and you'd get a mark for the working out, but you wouldn't get a mark overall. So it might be easy for you to put it into standard form. Your calculator might do that automatically already, but it's a good habit to get into. Use the following information to calculate the energy needed in the following situation. So now we're doing specific latent heat of vaporization. We have water is 2,257,000 joules per kilogram. Aluminium is 10,500,000 joules per kilogram. So how much energy is required to convert 1 kilogram of water at 100 degrees to steam at 100 degrees? How much energy is required to convert 85 kilograms of aluminium from a liquid to a gas at the same temperature? How much energy is released when 50 grams of steam at 100 degrees condenses to water at 100 degrees? So, next question. 398 joules of energy is needed to turn 500 grams of liquid nitrogen into a gas at minus 196 degrees Celsius. Calculate the specific latent heat of vaporization of nitrogen. So we're going to need to do some rearranging for this question, but we're going to still do the same structure. So we're going to write out our equation. E equals mL. We know that E is 398 because it tells us here that it's 398 joules of energy, so I'll write that underneath. The mass is 500 grams. 500 grams is 0.5 kilograms. So 0.5 times L. We want to get L by itself, we want to make it the subject, so we need to do the opposite of multiplied by 0.5, which would be to divide by 0.5. Whatever we do to this side, we need to do to this side. So we need to do 3.98. Oh no, 398, I apologise. Divided by 0.5 will give us L. $796. So 796 joules per kilogram. Calculate the specific latent heat of fusion if 183,600 joules is supplied to turn 3.4 kilograms of solid sulfur into a liquid at 115 degrees Celsius. So sometimes you are expected to bring together ideas from different topics. We split them up into different topics, but in the exam this would all be in paper 1. So P2, where you learnt about specific heat capacity, could come up in the same topic as where you would find specific latent heat. So we're going to recap that a bit so that you can, because then we're going to do some more complex questions after this. So recall from P2 that the energy required to change a substance's temperature is given by energy equals mass times specific heat capacity times temperature change. E equals mc delta theta. So E being energy, M being mass, C being specific heat capacity, delta theta being temperature change. So how much energy is needed to raise the temperature of 2 kilograms of copper from 0 to 10? The specific heat capacity of copper is 380 joules per kilogram degree Celsius. A hot water bottle is filled with 0.8 kilograms of water at 80 degrees. During the night it cools to 30 degrees Celsius. The specific heat capacity of water is 4,200 joules per kilogram degree Celsius. How much energy has it given out? And then I've got two temperatures. Remember that delta means change in, theta is temperature, so change in temperature. Whoops. How much is the temperature changed by? So I need to find the difference between these, which would be 80 minus 30. Now, some of you might already be able to just kind of spot that the difference is going to be 50 degrees because you might be good at mental maths, but it's fine to put it into your equation like this. I would rather you double checked, I'd rather you did it on your calculator than you relied on mental maths and in the stress of an exam or assessment that you just made a simple error. Calculate the total energy needed to raise the temperature of 5,000 grams of water from 55 to 100 degrees Celsius and then to turn it to steam. Specific heat capacity of water is 4,200 joules per kilogram degree Celsius. Specific latent heat of vaporization of water is 2,300,000 joules per kilogram. This is a bit more of a complex question, and I've definitely seen GCSE questions that are very similar to this before, if not almost identical, just a different scenario. So let's remember that specific heat capacity of water is going to be energy to raise the temperature of the water, okay, and the specific latent heat of fusion is going to be when it changes state. These two equations, the ones you get given, I've written them here so that you can recap them. So what we're going to want to do is to know how much energy is required to heat the water up, and then how much energy is going to be required to turn it into steam. So we're going to need to find the sum of these two. We can do it in 2 steps. So now we have these two amounts of energy. We want to find the sum of these two. So this symbol just means sum of, okay? You will need to use data from the table to answer the question below. Using the values from the table above, calculate how much energy is needed to turn 1 kilogram of ice into water vapour if the ice starts at a temperature of 0 degrees Celsius. So we're going from ice into water vapour. So let's think about this step by step. First of all, I have ice, and this needs to turn into water. Okay, and for this we need to use energy equals mass times specific latent heat. Then I need to get that water from 0 degrees Celsius to 100 degrees Celsius. So I need to do energy equals mass times specific heat capacity times the change in temperature. And then I need to turn that water into steam or water vapour, for which I'm going to need to do energy equals mass times specific latent heat of vaporization. This is latent heat of fusion. So I can do these three calculations individually because it's all the same mass, it's 1 kilogram of mass. I just need to make sure that I'm really careful about the values that I use for each of these calculations. And I've been given plenty of space at the bottom. So let's just work through this. These boxes that we've put into the booklets and that you'll have the pages for are really useful in terms of doing step by step. So read through the question and pause the video. Have a go at the question yourself, okay? And then if you need help, go back, have a look at the step-by-step bit here and then come back and mark it afterwards. An ice cube has a temperature of minus 15 degrees Celsius. The total energy needed to raise the temperature to 0.0 degrees Celsius and completely melt the ice cube is 5,848 joules. Calculate the mass of the ice cube. Got a specific heat capacity of ice is 2,100 joules per kilogram degree Celsius, and the specific latent heat of fusion of ice is 334,000 joules per kilogram. So let's think about it like this. The total energy needed is going to be the same as the sum of the energy needed to raise the temperature to 0 plus the energy to melt the ice. Okay, so the total energy, which is 5,848 joules. Okay, we do know the total energy. The energy needed to raise the temperature to 0 degrees Celsius. Well, if we're raising the temperature, that is the specific heat capacity equation, which is mass times specific heat capacity times the change in temperature. And to melt the ice is the specific latent heat equation, which is mass times specific latent heat of fusion. Okay. So what you might know in algebra is because I have mass multiplied by two things plus mass multiplied by something else, I could put this into brackets so that I have that my energy, so 5,848, is equal to mass multiplied by specific heat capacity times the change in temperature plus the latent heat of fusion. Okay, so we can think about this the other way around. If I was to multiply these brackets out, I would do the mass multiplied by this plus the mass multiplied by this, and then I would end up with this top line back anyway. Okay, so now we can substitute in our values. We only have one mass, which should then mean that we can work it out. The thing I will say is, in terms of like bid mass, make sure that you are considering these two together. Okay, so it's definitely specific heat capacity multiplied by delta theta plus latent heat of fusion. So the first thing that we're going to do is we're going to solve whatever's in this bracket, because otherwise it ends up being a little bit messy. We've got m times this number, and we want m by itself, so we're going to divide by this number. If we do that to this side, then we need to do that to this side as well. So I don't really have space to do it here, so I'm just going to do it on my calculator. Specific latent heat of fusion or vaporization is the energy needed to melt or boil, if it's vaporization, 1 kilogram of a substance without changing its temperature. In latent heat calculations, use the equation energy equals mass times specific latent heat. The specific latent heat of ice or of water can be measured by using a low voltage heater to melt the ice or to boil the water.